Singularities. The delightful mathematical firestorm that occurs when we start to use some of the answers to the Einstein field equations. But apparently, black hole pioneer, Professor Roy Kerr, one of the solvers of the Kerr-Schild solution to rotating black holes, he seems to disagree. Well, you all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one rule he had. I don't think it rules them all, and it might be just hyper-rulal turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rulal turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Black holes might not actually contain singularities. The physicist in question is Roy Kerr, who's famous for his contributions to general relativity. He was
that was the guy we were just talking about. Thank you, Dr. Hassenfelder. Links, of course, to the video in question, the doobly-doo. I first heard this, I think it was probably about a month or so ago. At least it says 4 weeks ago there. And then, of course, our good friend, Anton Petrov from the Anton Petrov channel, he covered it a few days ago. So let's just jump into it right here. Boom.
First to understand how to...
Oh, wait. No. That was the wrong one. I was sharing Dr. Hassenfelder again. Welcome to live internet. All right. There we go. That's the one. There.
And these Schwarzschild black holes make sense mathematically, but potentially not physically, ones. And may not really exist in the actual universe.
Never seen them.
And that's because all black holes we've discovered to date will usually spin and are also expected to contain charge as well. And so he proposed the concept of
this is the cool thing that you kind of get from the Kerr Solution. We'll get into that. You basically get an ellipsoid there. Thank you, Anton. Okay, so what's all this hubbub about? Now, full disclosure, I am totally biased here. And this happens to be one of the areas where I happen to have a bit of a difference of philosophy than, say, Thad, if you would there. Could just be because I'm a very simple dude. And I'm just like, wait a second. You got a neutron star. It's spinning in there. It should basically be a black hole. It almost all I know is you add mass to a neutron star, apparently it gets smaller. You add mass to a black hole, it gets bigger. What does that mean? I don't know. It sounds like a point of maximum density. Thank you, Jen. So what are we going to get into right here? So what we will get into right now is we have some links here to the different things on the doobly-doo. And most of these are basically just because of Anton and Professor Dr. Hassenfelder there. So let's go to our window here. All right. So here's the original paper that apparently contains the singularity theorem that Professor Kerr's big thing is there doesn't seem to be an actual proof of this. If you're saying this is mathematics and everything, his big thing is he claims a lot of relativists are confusing affine distance with geodesic distance. I just remember, again, I ain't a mathematician. I ain't a professionally trained physicist or something. I've probably watched, I think, about 173, 178 episodes of Professor Wildberger's Insights at the Mathematics thing, plus the ancillary videos. And the big things that you learn about from like the ancient Greeks is they didn't like to do distance. They're like, all right, we'll do the angle, we'll do this, but they tended to be very hesitant of it. So if you want to go into this, the whole gist, at least I actually haven't full disclosure read this paper, but basically, let's say you had gas and it just were to collapse and it collapsed, and then it would be a point of infinite density and infinite small, and the mathematics goes awry. I mean, if we are going to assume that there is something going on within there, personally, I figure I'm like, all right, we would have to have a minimization, some form of minimal form. If only we happen to know of a minimal form within, let's say, maybe a 3-manifold that could do that. Not like we could try to Google that or anything. Now, we're going to go. This was actually really fascinating, and this is looks like from a Colorado educational site. This is something that Anton had listed here, and I think this is very interesting just because he's like, black hole is a waterfall of space. And they're literally showing the Ren and Stimpy episode where they're going in there and things get all wonky, and that's mostly satire, we think. Misleading picture. And actually, it was John Mitchell who was one of the first proponents of dark stars, if you will. It's like, all right, if you had a density of mass sufficiently enough that it's like, well, if the escape velocity it ends up exceeding the speed of light, then you're not going to see any light. It's basically going to be invisible. This was in 1784. It was published in, like, I think the Royal Letters of the same thing that I think Professor Gupta was published in last year, and now has become free source. Actually, I believe. Hey, thank you guys for making education and knowledge available. Okay, so basically, I've heard Leonard Susskind kind of describe black holes as this. It's like, all right, suppose you're a fish, you got like a whirlpool, a waterfall, whatever, and you can swim. This fish is basically like a photon. It's like trying to navigate around. If all of a sudden the water is just going so much faster than the fish can swim, you're not gonna. The fish can say all its fish things in there and go blub blub blub, but none of those blubs will ever get out. Why? Because the water is just going so dang fast. It ain't gonna carry your sound waves, and that's generally, perhaps incorrect, the general gist that you get for like the speed of light falling into everything there. So okay. So the Schwarzschild solution is this is the thing you saw Anton had there. It's basically nothing is rotating. Because remember, it's all perfectly still. It's not like this no true still point, except for maybe a 0, 0, 0 coordinate, something like that. Conjecture on my part. But so you got everything, it just falls in, and then you would have a singularity. It would just keep on falling and falling. I'm like, wouldn't it go inside out? Maybe it's leading to a white hole somewhere else. I don't know. I haven't visited a black hole recently. So, but okay, yeah, that's solution. And you have those kind of other ones. So it's like, all right. So rather than, I think, increasing, because you can see it gets faster there, it's basically just going to do the same thing there. So now you have an inner horizon, outer horizon, the riser Nordstrom waterfall. The wormhole waterfall, they basically just reflected it over there. And the Kerr waterfall. As you can see, it's kind of more of an oblong. And they're saying it's a ring singularity. I heard that. I've heard PBS Spacetime say that as well. And Professor Kerr seems pretty adamant. He's like, I never said there was an actual singularity. He's like, we take that, and then we assume, okay, what? We got like a star there. We got a super dense glob of mass there. And if it's spinning really fast, basically, eventually you get an event horizon there. So, and then they have the Kerr antiverse thing, which I don't even know. I don't know. Is this going into a white hole or something there? I don't know. Okay, so we have the actual paper here. What I'm going to do is I'm going to bring up my other paper here because what I did is I downloaded it because you can download it, of course. And this is the Professor Kerr one. Okay. I actually highlighted some points. It's 19 pages long. I actually read through it. I did some of the maths. I at least kind of went through it and everything. Again, I am not a general relativist. I did not come up with any of these solutions or anything. I am a dude on the internet that finds these things fascinating. So, I'm sorry. I am ignoring my chat just because I just blather on about this and that. But welcome, Kali. Kali, nerdy. What's going on, my friends? Kali, my personal opinion on this, and I'm not saying this is reflective of the whole monastery and everything. I tend to think, all right, once you get to a certain point, it's like, all right, neutron star stops compressing. You had a maximum point of density, approximately Planck length over the Planck mass over the Planck length. Planck mass is 10 to the -8 kilograms. Planck length is 10 to the -30. Ridiculous orders of magnitude. One is a maximum, one is a minimum. You divide that, essentially you get like the Schwarzschild metric and stuff like that. To the best of my knowledge, again, I might be off by a pi or two. But on those magnitudes, it's a lot. But the interesting thing is, it depends. Are we talking about a Rick rotation? Because I think that's one of the, I keep hearing about this. It's like, all right, I heard that Professor Hawking said, this is a trick. It's only a trick. And then he bases things later in his book on the Wick rotation trick. So it's like you're spinning time around. It's like, it might work mathematically. But as we saw from the thumbnail, Professor Kerr at one point is, yes, we need physics, not just mathematics. It's an amazing thing for a physicist to say. Imagine my shock. But so this was published on December 5th, 2023, so last month. Okay. The abstract. There is no proof that black holes contain singularities when they are generated by real physical bodies. Roger Penrose claimed 60 years ago that trapped surfaces inevitably lead to light rays of infinite fine length, or false. Penrose and Hawking assert that these must end in actual singularities. When they could not prove this, they decreed it to be self-evident. It is shown that there are counterexamples through every point in the Kerr metric. They are also asymptotic to at least one event horizon and do not end in singularities. So essentially, the whole point he's essentially communicating, he's like, apparently, and don't get me wrong, I like Professor Penrose, and Professor Hawking led a very interesting life. Leave that up to folks themselves. But basically what he's saying is, they're saying, well, we have this math, so this is what it is. It's like, do they actually know that? It seems, I think that's why it's a theorem or a conjecture. And a lot of folks are like, well, there's singularities there. And he's like, that's not what I said, folks. He's like, I never said there were actual singularities. Like, yeah, so we get this interpretation, but what's the physical interpretation? Because apparently a lot of things based on singularities they're also assuming, like, I don't know, 19th century physics and equations of state and everything. If we're going to say there's quantum mechanics and stuff going along, it's like, do you really have any idea what's going on? And he's like, if you have a proof, that's fine. But if you're saying that, well, this holds because it's evident, his whole thing is if you find one counterexample, well, that's not actually like a law or something like that. It's, you can say maybe this is true, but doesn't actually cover it. So we'll all right, so we got about at least 18 pages more, so we'll go through this quick. So basically they're talking about the Schwarzschild metric was the first thing. That's for the non-rotating black holes and everything. And they're talking about, oh, is this inevitable and everything? So apparently they developed, him and Schild developed the Kerr metric, constructed in 1963, soon after the discovery of quasars. It has a singular source with angular momentum, as well as mass surrounded by two elliptical event horizons. These regions will be called the event shell, for want of a better name. Objects enter this are compelled to fall through its interior. Like Kerr itself is source free, generated by a ring singularity server. It cannot be singular, since GR would then emit smooth, Park-like solutions of the Einstein equations that are purely gravitational and sourceless. The ring singularity is just a replacement for a rotating star. So again, he's saying that this ring singularity that I've seen people present everything is just a replacement for a rotating star. Is he correct? I don't know. I just happen to know he has to have a solution of at least the black holes that we seem to observe in reality as best we know it. They all seem to be spinning. So it's ultimately, it's like you have that Schwarzschild thing. That's cool. Again, it is an exact solution to the Einstein equations based upon what people have told me. Does that model what actually happens? Because everything seems to be spinning or something like that. So we continue. All right. The consensus view for 60 years has been that all black holes have singularities. There is no direct proof of this. Only papers by Penrose outlining a proof that all Einstein spaces containing a Trepp surface automatically contain false. Basically, all those lines kind of just coming together at some point. This is almost certainly true, even if the proof is marginal. It was then decreed without proof that these must end in actual points where the metric is singular, in some unspecified way. My personal opinion is if there was something going on in black, I just think it's just a big hunk of mass. And it's all gimbal locked together, and it's like, well, if you consider like a period, depending on the observer, to be a singular point, I don't know. Is that essentially a two-dimensional or three-dimensional just point to 3 plus one-dimensional observers like us? I don't know. And again, it's conjecture on my part. Plenty of people disagree, and that's not even what he's saying here. He's basically just saying somewhere in the center, you got a super dense thing of matter. Okay. Nobody has constructed any reason, let alone a proof of this. The singularity of believers need to show why it is true, not just quote Penrose's assumption. I'm just saying that if you're going to try to do some mathematical physics and stuff like that, is that what it's actually saying? Or are we just kind of basing this off of, well, Roger Penrose said that. He won a Nobel Prize. He's really smart. And people have been saying that for a long time before they have that. And I believe even was it for the Nobel Prize. I think the committee said extremely dense regions of space-time. I'm pretty sure they avoided the term singularity. So I also think, is there a hyperbolic title to this video? Yes, but when you read through this paper, Professor Kerr kind of really lets loose. This is kind of like one of those papers. He's like, well, the author is this. It is the opinion of this. I'm like, these are like the old school type of papers that I really like, because it's like, yeah, he's giving an opinion and stuff, but he's also backing it up too. And I don't know. He also has the clout that he can kind of get away with it. So just my observation there for this dude's opinion. Okay. So basically what they also did is they also kind of fixed some points, and that seems to be one of the other things. It's like you're making assumptions that there are fixed points, and then you need to have at least a third or a fourth point to try to correlate things. I might be butchering this, but he basically is giving the history in him. Because he was literally this. So let's just read this part here. After the first Texas Symposium on Relativistic Astrophysics, November 1963, Ray Sachs and I tried to construct an interior solution for Kerr by replacing its ring singularity at r equals 0 and z equals 0 with a finite non-singular interior metric with outer boundary at r equals 0 is greater than 0, say, lying inside the interior event horizon. We started by constructing the Eddington-Christoffel type coordinate that we were independently calculated by Rob Boyer that year. And believe it or not, they were using preprints back in the day. It's like, oh my God. It's like, imagine the power of preprints. Like, well, this hasn't been published. We're not sure. We have access to this. Seems to give us some interesting results. Let's give it a shot. So, we use a preprint of an outstanding paper by Professor True on stationary, the axiometric Einstein spaces, which showed that if these are asymptotically flat with no singularities at infinity, they can be almost diagonalized, i.e. put in a form containing only one off-diagonal term, the coefficient of d phi dt. Kerr satisfied all the required conditions. Pay note to this. This comes up later, because the whole diagonalized thing, it's like, all right, so like, if you got like a matrice or something, very often we'll have everything as zeros, and it's like, all right, just diagonal terms there. And then there's one off diagonalized thing. That's what I'm interpreting from that right there. Well, experiments, that's a fantastic question. I'm not sure we actually want to do those experiments. Computationally, maybe we could try them, nerdy. It's just, if you're going to try to, it reminds me of an episode of Young Sheldon where at one point, one of his mentors gets fired because he mentioned when he was going to work at the particle accelerator at Texas, he's like, well, there might be just a minuscule chance that we could create a black hole and it could just consume the Earth. They get fired for that. And then later at one point, they're going through and it's like, TV warning, a black hole has been created. It's absorbing everything. And they're going into, well, that might just rip apart that particular Earth, but we may be in some multiverse where it's like, we might just flash through and we wouldn't even know it happened. And they left that up to interpretation. I respect that. I don't know. I'm not an experimentalist. I'm open to ideas. But, okay, we will continue with Professor Kerr. Okay. So basically they keep on, he's going through his literal process of like working on this back in like the 60s and stuff like that. And it's been, oh my God, it's literally been 60 years since I think they came up with that Kerr solution. The man has a lot to say. Okay, so they're going through. He's Penrose outlines a proof that if the star satisfies a certain weak energy conditions as a trapped surface, then it must have at least one fault. Basically, those lines coming together at some point or coming towards some form of a geodesic or affine point that may be somewhere. This is true, but it's literally more than the hairy ball theorem. That's basically black holes. Do they have hair coming off or something like that? And I don't know this, but as somebody that's a troll at heart, I feel like he's kind of trolling and in a way trying to get people to think, because he even says, he's like, ultimately at one of the footnotes, he's like, what does this all mean? He's like, I have no idea what this means. He's like, it sounds like something that a postdoc, a really bright postdoc, might be able to work on. So I think it's a call to action. It's like, maybe somebody should try to figure this out. But you'll continue. All right. All the examples of those falls given in this paper are similarly asymptotic to an event horizon. They arise because the interaction between the light-like killing vectors that are the normal to the event horizon and therefore lie inside them. The light rays that approach these tangentially, giving converging pencils. They're basically points that are going to continue to go down, like when you sharpen a pencil. Okay. So what the heck is a killing vector? It's actually kind of fitting in a number of ways, and it was. Let me go back over here. We need to. This guy. All right. Boom, over here, and all right. So the killing vector field. God, it sounds so brutal. It was actually just named after the dude that figured it out. In mathematics, a killing vector field, often called a killing field, named after Wilhelm Killing, is a vector field in a Riemannian manifold or pseudo-Riemannian manifold, that preserves the metric. Killing fields are infinitesimal generators of isometries. That is, flow generated by killing fields are continuous isometries of the manifold. More simply, the flow generates a symmetry in the sense that moving each point of an object the same distance in the direction of the killing vector will not distort distances on the object. So it's a way of preserving the metric. What the heck is this? I guess something like this. Okay. Killing field along the circle, flowing along. This is probably the best way to... So basically, you have the vector field, it's going to do the swirly thing. So basically, it's just continually deforming. So basically, you can keep your things satisfied. All right. So I'll stop that. Oh, and let's just get into this real quick. The funny thing is, at least for me, I'm just able, when I just type in affine distance and affine or geodesic distance over here, the answer at least Google gives me is the best one that I can use to differentiate it is, let's see. Okay. The affine distance for two elements tangent to a parabola. Ooh, parabolas are important, I guess. Is equal to the affine arc lengths of this parabola. Affine parameter. In a three-dimensional equiaffine spice, the affine distance may also be defined in terms of elements along pairwise incident points, straight lines and planes. All right. So basically something kind of on a graph, because you're modeling. Because I've at least seen like those Penrose diagrams where it's like, all right, you go down, they cross, you're on this side of the event horizon, you're on that side, yada, yada, yada. Geodesic space. Formally, the geodesic distance between two vertices is the length in terms of the number of edges of the shortest path between the vertices. With two vertices that are not connected on a graph, the geodesic distance is defined as infinite. Okay, so basically it would take forever to get... Basically, if you're talking about geometry, it's the shortest actual distance you have to do in space as we know. That's what I'm taking it as. Hey, could be totally wrong, but all right, we'll go back to Professor Kerr's paper we have marked up there. Okay. Yes, things doing stuff. Oh, and Kali, if you get a chance, you may want to listen to Professor Green's World Science Festival thing on the state of string theory. They had Professor Whitten there. Professor Whitten said some things that, depending on how you take them, is like, it's worth watching, I would say. But okay. Okay, so they go through again without going through the whole paper. Okay. As Einstein once said, general relativity is about forces, not geometry. Ooh, this may be a simplification, but it's a very useful one. As we highlight over here. Most probably all believe this standard model is non-singular for neutron stars, but not for black holes. Why the difference? The actual density can be even lower for a very large and fast-rotating black hole interior. See, that's the interesting thing. It's like you hear about these neutrons. They're much larger than they should be. Or it's like, we're getting this reading from a galaxy far, far away. What is this? It's either a neutron star or a black hole. Why is it hard to? Well, we judge by the mass. Well, sometimes it's not always that. Sometimes we get weird results. It's like he gets into this a little bit more later. So for brevity's sake, let's go through. I mean, again, it's only 19 pages, and there is math, but it's actually not a huge amount of math. A lot of this is literally just him, just kind of like talking about his process of going through things. So, pardon. He goes through. He's like, anyone who does not believe this simply needs to supply a proof. Long story short, he's like, all right, if you don't believe the words coming out of like Professor Kerr's mouth or on this paper here, he's like, simply provide a singularity proof. That's rigorous. I mean, if it's true, we don't really know what's going on. So it's like you have a certain number of assumptions, and he does get into that too. All right. So the affine parameters. The short section is the crux of the argument that singularity theorems are proving something different to singularities exist. With an exclamation point in quotes. The reason that so many relativists have assumed that Raychowdhury's theorem proves that bounded affine parameter lengths lead to singularities is that they have confused affine with geodesic distance. They're very different concepts. Geodesic parameters are defined by first-order differential equation. All right, that stuff there. So you get your G mu nu and everything. D is an arbitrary parameter along the ray, perhaps time coordinate. So in particular solution, C is an arbitrary constant. This does not work for light rays where ds equals 0. Its replacement affine distance is defined by a second-order differential equation instead, since the acceleration is proportional to the velocity of the geodesic. You got that stuff there. Our lambda is a function on code. Okay. Some of the things he says is just, it's a beautiful thing. Okay, we continue. The crucial difference between these two parameters, S and A, is that if lambda is a constant in equation 2, then A of 0 equals E lambda of t, and t is bounded at either plus infinity or minus infinity. This is also true if lambda is bounded away from 0, with the absolute value, yada yada, where B of 0 is a non-zero constant. This has nothing to do with singularities. So here's the killing vector, so basically that twirly thing over there as well. Okay. So here's the Shoutout editing for spherically symmetric Einstein space there, yada yada. Let's see, it's a mass. Okay, we'll do a little bit of mass in the next thing there. And again, this is just my first. Basically, he's going through your different solution. You can get the black hole, you can get the white hole, you can get different variations of them. So those paired, basically light vectors or whatever vectors you're going through there. Basically, he's saying that rather than just being a singularity, it might just literally end up on the polar other side of where it came in from. That's what I took away. So, all right. Since the metrics are stationary, this is an example of the predictions of section 2, where I think you're talking about the affine geodesics. This contradicts the basic assumption that all singularity theorems are based on. The only reason it is assumed that these rays must end at a singularity is so that these theorems can be proved. This include Hawking's, Penrose's, and other similar theorems for black holes and the Big Bang. They are built on a foundation of sand. This is why the video has the title it does. Because he's just like throwing all this stuff that a lot of folks like are assuming or saying it came from this, some primordial singularity. How did it happen? Quantum fluctuations. The hand waving is built in. Again, That might be harsh, might be wrong, but this is a pretty notable dude who's contributing back to the conversation. Thank you, Professor Kerr. All right, so they're going through the different coordinates here. I highlight this part because each of the coordinates u and v is constant along the promotional v and v, those whatever vectors you want to have there. But v is useless near the event horizon and r equals 1 because it is singular there. I'm like, that's the point where I'm like, wait. So if all of a sudden you hit this and you're hitting the point where it's singular, at the event horizon, basically the place where after that we don't know what goes on. The thing that also increases, like it's like, all right, throw a neutron in, throw a neutron in, throw a neutron in. And then by that total amount, each value of Planck mass will have like 1 Planck area or something like that. It's like, okay, so it gets bigger, it gets bigger. I'm like, what if all that matters is maximum density? It's all locked together. So you got mass, you got some space, because it's got a radii and everything. I hear people say that time doesn't exist there. I mean, like, if it's not experiencing time, then does that mean there's any oscillation? Is that just the maximum matter? Whether that happens, I just think it's really just a giant pyramid, just period there within space-time as we know it. And if it rotates, it's going to be spinning stuff around. It's so massive, it's going to do funky things. That's why I previously conjectured, again, just a dude on the internet, black holes are actually the most boring things in the universe. I want them to lead to other realms of persistence that we can go through and child. That'd be so cool. But I'm like, the simplest explanation. It's really just a big, dense clump of matter. Now, the effects it does, if it's spinning near the speed of light, those can be fantastical. Absolutely. But I think those are the effects from it, not necessarily it itself. It's just the effect of it spinning. Conjecture on my part again. All right. Okay, so we get into, all right, see these different symbols and stuff. Okay. If one believes in 19th century equations of state, regardless of pressure, then anything is possible. Footnote 9. What this all means, I have no idea. I do not believe anyone else does either, since the behavior of quantum matter at such extreme pressure is unknown. Well, it takes Professor Kerr to tell us that we don't know what's going on. I tend to agree. But also, black holes form in our universe when matter accumulates in the clumps. They are too massive and or too dense. They do not start off as white holes a la Christoffel. So I guess one of the solutions up here, it's like, oh yeah, you get a black hole, you get a white hole. It's like, but are you basically saying like it starts off as a white hole and it goes into that? Like, maybe there is evidence. Maybe we haven't seen it yet. Maybe it isn't really the physics that we're looking for. I don't know. Again, totally biased. Ooh. Okay. So, this is a cool part. All right. Suppose that there is a non-singular spherically symmetric star, S, at the center of Eddington, and suppose it's bounded by R equals R0. All the incoming P and Vs, all those things that are happening, are radial geodesics passing through the central point and dying on the opposite side of the star. Since the radius is an affine parameter on each ray, the total affine length from crossing the event horizon is less than 4m, a finite number. The possible of infinite curvature at the center has nothing to do with the singularity theorem, just the claimed physics of the star. The affine parameters are irrelevant. That's why when he actually does a calculation for the affine things and be like, okay, you can get this. He's saying that this isn't what's actually happening. He's like, this isn't evidence for this. You can assume that, but you haven't proven it. So it gets into the Kerr metric here. So I think we have a little bit of math here. Okay. He goes into how they figure this out. This is, all right. The Kerr metric was discovered in 1963 by imposing the following series of conditions on an empty Einstein space. Number 1, contains a field, K of mu, of geodesic and shear-free light rays through each point. Goldberg-Sachs theorem proves that this is equivalent to demanding that they are repeated eigenvectors of the conformal tensor. So basically, copy, paste, copy, paste. You just keep on going through. This gave a set of 5 partial differential equations, which were inconsistent unless an endless chain of further integrability conditions were satisfied. This led nowhere, so 3 more simplifications were opposed in sequence. I just thought it was interesting. There was 5 partial differential equations. I have no idea what those might be in regards to. Number 2, it is stationary. Independent of time. The help of the equations were still intractable. Number 3, it is actually symmetric. Much better. Assuming symmetry. All right. 4, finally, it is asymptotically flat. Okay. The symmetry conditions reduce the problem to solving some simple ordinary differential equations. The final assumption. 3, eliminate all possibilities, including nut space. Oh, that was another thing that he may or may not be trolling about. That's an actual thing. Continue on. All right. So basically, when A is 0, A equals 0, the coordinates, basically you have 3 of the coordinates which are just spherical polars in Euclidean space in the metric reduces to Shoutout kinetic transformation. Basically, I think what he's saying is says something is off diagonalized. I think this is where the important part comes in. He's like, it can't necessarily be singular, because at one point, I think one of the assumptions and some of the derivations is, all right, we're assuming a fixed point here, we're assuming a fixed point here, and then if we do the right math, we can get more fixed. Again, just my noob analysis. All right. The surface of constant R are confocal ellipsoids of revolution. All right, so he gives this equals 1. All right, so we actually have this. That's good. And that was easy enough math I could just throw into Wolfram Alpha. So we'll go back over there. So what is that picture that he's talking about? Let me go over to you. Okay. So basically he's talking about this, an ellipsoid. Boom. You just plug in the things that he had right there. It's a surface. Oh, it's that ellipsoid that he was talking about. Okay. That's cool. And then they go into I'll stop that. Well, I actually need to go back to read this part because this is interesting. So it's a little bit more math after that. All right. So simple calculation shows that the vector k of mu is a geodesic in the underlying Minkowski metric as well as a full metric. All right. So this is true for all Kerr-Schild metrics. Those P and V's that lie on the equatorial plane are tangential to the central ring. So when you get this there, the rest all pass through this to a second non-physical sheet. The metric is non-singular except on this ring. All right. So what happens when we plug that in? This actually gave an interesting result for, you'll see. Because, all right, so we got our oval in there. So remember, it's saying on the ring. This is what we got. This geometric figure is a circle. I mean, that looks like it. That looks like a double cone to me, personally, but depending on, they're doing the 3D contour plot, but if you looked at it from perhaps 2 dimensions at any one point, I mean, isn't that kind of a circle? I don't know. I just found that very interesting that literally just came back. It's like, oh, you're setting that out, because then if you divide that out, you kind of equal what? Again, could just be bad maths on my part, but I think yes, space egg. Oh, Moxbit. Oh, Collie. No, that's going to be the next video I had meant to do. I still need to read in response to Dr. Unzicker's video where he was talking about the biggest problem in gravity apparently solved. I am also biased on that because it also seems like a more of a formalization between Professor Sharma and I think I read most of his paper, and I need to read the young postdoc's paper as well. So, all right, we go back to our little markup version here. All right. We have that. All right. Again, there is no singularity problem when the ring is replaced by an appropriate star! Exclamation point. He's like, okay, there's no singularity problem. He's like, you take this ring. All right. You put the star that was collapsed in there. Boom. You don't need a singularity. So the links are in the doobly-doo, Kali, for most of these papers and stuff. You don't need to have any journal access or anything that I saw. All right, so I love this part because he's just straight up giving the history about like what happened. So he's going over this. They do this huge. This whatever this is. You're trying to balance out the total summations of all these different derivatives or whatever it is there. He's like, we stared at this metric for a very short time, gave up and went for coffee. The problem is that there are too many possible interior solutions. The same as for regular neutron stars. Physics is needed, not just mathematics. That's where I pulled that quote for the little thumbnail there. All right, conclusions. The fact there is at least one fall in Kerr, the axial one, which does not end in a singularity, shows that there is no extant proof that singularities are inevitable. The boundedness of some affine parameters has nothing to do with singularities. The reason that nearly all relativists believe that light rays whose affine lengths are infinite must end in singularities is nothing but dogma. Wait a second. Is he saying that people just believe it because other people were saying it, so thereby it's an article of faith? Well, I mean, these are good scientists, so they would realize if that was the case or something. I mean, I don't until somebody usually tells me I'm wrong, but, and again, I'm going to do it in the internet. Here we go. Oh, this is fun. Because this is something that I always kind of thought about. I'm like, as a star shrinks, its centrifugal forces rise rapidly. Whether or not it's actually the centrifugal force discussions. That aside, there is no known reason why there cannot be a fast rotating non-singular star inside the horizon generating the Kerr metric outside. There is no published paper that even claims to prove that this is impossible, and yet so many believe all black holes contain a singularity. I did, but we continue on. And he's like, okay. This is a very important point. It is very much a do-it-yourself paper where the reader is supposed to prove the more difficult parts. Some of these may not even be true. He's admitting, he's like, hey, this stuff might be wrong. He's like, it'd be great if some smart young person could figure this out. Thank you, young people. Suppose we have a real star that's spinning fast, but is also shrinking and is on the verge of forming a black hole. There will be a shell surrounding it that is difficult but not impossible to escape from. As the star contracts further, this will become harder and harder until an event shell forms. Radial light rays that come down the axis through the North Pole will pass through the star and die asymptotically on the inner horizon on the opposite side. And he's straight up, he's like, I cannot prove this because there's no agreed solution for the metric inside the star. All right. So, and we finish the thought experiment here. If extra matter joins the star, e.g. from the initial supernova, then further collapse will probably take place. Unless the angular momentum to mass ratio rises very rapidly, the elder shell will become impenetrable and a black hole will form. This is the moment when the singularity is believed to appear. According to all true believers, no singularity before event shell forms, inevitable singularity afterwards. This is why I think I think this is what I would consider a noble troll. It's like, you're doing some trolling, but you have a point. You have a purpose. And Dune Man has enough clout that I think people are willing to listen. Or at least, hey, hear the dude out. What is the equation of state? Still a work in progress for a neutron star. I think, I think that's all we had right there. Cool. So, hey, Rosetta, good to see you. Yeah, we're just talking about how Professor Roy Kerr, one of the guys that helped provide the Kerr solution to rotating black holes and stuff, because basically all black holes, as far as we know, based upon our observations and equipment, they all seem to be spinning. So the whole Schwarzschild thing, it's like, all right, nothing's spinning, everything. Basically, that dude, actually 60 years after he papered the Kerr solution to black holes, he's like, I never said there was a real singularity there. He's like, yeah, I had a ring singularity in the math that I just assumed was just a super dense star at that point. He's like, if you just put a star in the center, you don't have any problem with singularities. And a lot of folks just kind of took Penrose's thought that he's like, well, this seems to be self-evident there. So a lot of folks are like, oh, that's good. Okay, singularity, difficult. We can't figure out. He's like, no, we just don't agree upon what's happening inside a neutron star, so we can't actually fully solve this. I'm like, that seems like evidence. How dare he? But when am I going to join? I don't know. I got stuff and things to do. It depends on what we're talking about and if I'm invited. But oh my God, I'm blathering on for 45 minutes of mathematics and black holes. All right, I need to get back to website design and finishing doing all these other calculations and reading another paper. But that's all we got for right now. Oh, LDG, I missed you. I'm sorry, my dude. Oh, I'm a terrible host. Sorry, I was reading stuff. But peace out, everybody. Take care of yourselves. It's a crazy world out there. But 2024, I hear, is a new door. Peace out.